next speaker of the morning is Felipe Rincón from the University of Warwick, and he will be telling us about positroids, non-crossing partitions, and positively oriented matroids.
All right. I want to thank the speakers, the organizers for this amazing conference. And I want to talk to you about positroids, non-crossing partitions, and positively oriented matrices. So this is some work that we've done with Federico Ardila and Lauren Williams. And then I'll start by reminding you about matrix. So here's the definition. A matrix on the ground set n of numbers 1 up to n is just a collection of subsets that we call bases, satisfying the basis exchange axiom. So this just says that if you have two subsets in your collection, two bases, then, and you have an element in the first basis but not in the second one, then you can find an element in the second basis but not in the first one that you can exchange for A and still get an element in your collection. Okay. So this is some combinatorial notion that is trying to abstract independence, and out of this axiom you can deduce that all bases in your matrix have the same size, and that's called the rank of the matrix. So the example you should have in mind is if you take a matrix A with entries in a field K, let's say it's an m by n matrix of rank n, a full rank m by n matrix. Then you can take your collection B to be just the subsets of the columns for which the corresponding submatrix is invertible. Right? So if you start with any matrix over any field and you consider this collection of subsets, that's going to satisfy this exchange axiom, and it's going to give you a matrix that we're going to denote by m of A. And just to be very concrete, I have a very simple example here. So here's a 2 by 4 matrix with entries in the complex numbers, say. And then that gives you a matrix, a collection of subsets of size 2 from the numbers 1 up to 4, just by looking at the maximal minors of these matrices that are invertible. So for example, 1, 2 is in your collection here because the maximal minor given by columns 1 and 2 is non-zero. So for example, 3, 4 is not in this collection because the maximal minor corresponding to columns 3 and 4 is 0. Right? So any matrix gives you a matrix, and matrices are combinatorial abstraction of this notion of independence. Now, what are positroids? So positroids are going to be a special class of matrix. You can define it in this way. So start with a matrix now with real entries, an m by n real matrix. And we say that the matrix is totally non-negative if all the maximal minors are non-negative. So you don't allow negative minors. They can be 0 or positive, but no negative maximal minor. And in such a case, if the matrix is totally non-negative, then the corresponding matrix is going to be called a positroid. That's what positroids are. Matrices arising from these kind of matrices. So for example, the matrix that we just saw is a positroid because it turns out that this 2 by 4 matrix is totally non-negative. Every maximal minor of this matrix is non-negative. All right? It's either positive or 0. Here's an example of a matrix that is not a positroid. This one here. So this is a collection of subsets, a rank 2 matrix on the ground set 1, 2, 3, 4. It is a matrix. You can check that and it comes from a matrix, but it's not a positroid. And how can we see that? Well, let's assume that you can find a matrix, a totally non-negative matrix that gives you this matrix, where this is the collection of maximal minors that are positive. Well, because 1, 2 is here, then well, by doing row operations, you can assume that the first 2 columns of your matrix look like 1, 0, and 0, 1. Because 1, 3 is not in this collection, that tells you that the 1, 3 minor is 0. So that means that this entry here has to be a 0. 1, 4 is in your collection, so that means that this entry has to be positive. 2, 3 is in your collection, so that means that this entry has to be negative. 2, 4 is not in your collection here, so this has to be a 0. And finally, you see that there's a contradiction with 3, 4 being in your collection because this minor is going to be negative. So if you take a matrix like this, that gives you this positroid, but it's not a totally non-negative. This is a matrix, but it's not a totally non-negative. Hopefully you guys see why this is a matrix but not a positroid. And positroids are maybe the essential object in the study of Alex Posnick of the totally non-negative Grassmannian. So each positroid gives you Positroids give you a stratification of the totally non-negative Grassmannian, and you can study the totally non-negative Grassmannian by studying these positroid cells in the Grassmannian. And in his study of the totally non-negative Grassmannian, he showed that positroids have a very nice, very rich combinatorial structure. And I'll say more. I'll say a little more about this. And also, positroids are much better behaved than general matrix. So you should think of positroids as a small collection of matrices that are much better behaved than general matrix. So one instance of this, for example, is for general matrix, if you consider the realization spaces, the space of matrices modulo row operations that have the corresponding matrix, those varieties can be completely horrible. So there's this Neff's universality theorem that tells you that in general matrix varieties can be really horrible, but for positroids, the positroid varieties are much better behaved. So they are, for example, Cohen-Macaulay, they have just nicer singularities. So here's a glimpse of the combinatorics involved in positroids. So it turns out that besides all the usual ways of thinking about matrix that we have for general matrix, like in terms of ranks, in terms of circuits, in terms of closure operators, there are many other ways of thinking about positroids that are much more manageable. So for example, Grassmann necklaces, decorated permutations, lead diagrams, Pleiadic graphs. And I'm not going to tell you exactly what each of these are, but if I did this correctly, these are 4 ways of representing the same positroid. So what is a Grassmann necklace? A Grassmann necklace is just a sequence of subsets or bases of your matrix that are close to each other. So for example, in order to go from your second subset to your third subset, what you do is you drop the number 2 and you add some other number. So you drop 2 and you add the 5. And then to go from the third subset to the fourth subset, you drop the number 3 and you add something else. To go from this one to this one, you drop the number 4 and you add something else. The 9, and so on. So it's like a cycle.
The first 2 are equal is...
Here you drop the 1 if it is in the subset and you add something else, but because it's not in the subset, then you just leave it the same. So the rule is that to go from subset I to subset I plus 1, you drop the number I if it is in your subset, otherwise you leave it exactly the same.
Can you compact it one?
I mean, yeah, you just repeat it twice in your sequence. So this is going to be the subset I sub 1, and this is going to be your I sub 2, and yeah, it might be that it's the same I1 and I2. You're allowed to have that. And hopefully, well, and you can encode such sequences of subsets, such Grassmann necklaces, by something called decorated permutations. So a decorated permutation is just a permutation of your ground set from 1 up to n, but you're allowed to have 2 different kinds of fixed points. You can have either clockwise fixed points or counterclockwise fixed points. So it's just same as a permutation, but now fixed points can be of 2 kinds, either clockwise or counterclockwise. And maybe you guys see why these 2 objects are in bijection. So there is a permutation here that is recording what is the number that you keep adding every time. So yeah, okay. And then the two different kinds of fixed points correspond to whether the element was contained in your subset or it wasn't contained. Yeah. So there's also another way of representing positroids by Pleiadic graphs. Pleiadic graphs are planar bipartite graphs that look like this. So they have a boundary that is around the circle, and then it's a planar bipartite graph. All these vertices in the boundary have degree 1, and these equivalence classes of these Pleiadic graphs are in bijection with positroids. Another way of thinking about positroids is via their lead diagram. So a lead diagram is simply a filling of a Young diagram with zeros and pluses, and they have to satisfy some special condition, some kind of L condition that I'm not gonna tell you about this. Okay, but the point is that there are many combinatorially nice ways of thinking about positroids, and there are lots of beautiful combinatorics involved in all these objects. And this is by far this is not a complete list at all. So there are many other combinatorial ways of thinking about these guys, juggling patterns and rank tables and pipe dreams. And I think every time we know more about new combinatorial descriptions. But one description that I like a lot of matrix is in terms of their matrix polytopes. So what is a matrix polytope? Given a collection P of subsets of the ground set, you can define the polytope gamma B to be the convex hull of the indicator vectors of your subsets. So here I have an example. This is the same matrix positroid that we had in the previous example. Each subset, you can associate an indicator vector, a 0, 1 vector that tells you what are the elements in your subset. So 1, 2, for example, corresponds to the vector 1, 1, 0, 0. 1 is in, 2 is in, 3 is not in, and 4 is not in. 1, 3 is 1, 0, 1, 0, and so on. So each subset gives you a vector in R4, and then you take the convex hull of those vectors, and that gives you a polytope in Rn. And this very nice theorem of Gelfand and Sergenova tells you that the collection that you started with is a matrix. It satisfies this exchange condition, if and only if all the edges of your polytope are short, in the sense that they have the form EI minus EJ. So you only see edges between subsets that differ in one element. So here there's an edge. You remove one in the second coordinate and you add a 1 in the first coordinate. You don't see any long edges like from this vertex to this vertex. There is not, you don't see an edge. That happens because the collection that you started with is a matrix. What we found, and this also appears in work of Lam and Posnikov, is that you can characterize positroids very nicely if you look at their matrix polytopes. So among matrix, you can tell if your matrix is a positroid or not by looking at the facets of the polytope. If all the facets are intersections of the polytope with hyperplanes that look like this, so some coordinates equal to some I, but the crucial condition is that those coordinates that you're summing over have to form a cyclic interval. So a cyclic interval is just an interval of an interval of the numbers 1 up to n, but you're allowed to wrap around n. So think of the numbers as in a circle 1, 2, 3, 4, 5, and then any interval in this circle is going to be what we call a cyclic interval. For example, 9, 10, 1, 2 is a cyclic interval.
So the I has two different meanings, I suppose, and the EI.
Yes, this should be a S or something. Yeah, sorry.
And the EI is some integer.
Just some integer. Yeah. This is going to be the rank of this subset. But yeah, just some integer.
Does the facet condition imply the edge condition?
No, you can have facets. Yeah. So this is just for matrix. I'm assuming that among matrix you can distinguish positroids by looking at the facets that are cyclic intervals. And this is a result that we use for several other. This is like a key result that we use for several other things. So how do non-crossing partitions come into the picture? Well, I have to tell you about connected components for matrix. We call a matrix disconnected if it can be written as the direct sum of two other matrices. So M1 direct sum with M2, and that's by definition just the bases are the disjoint union of the bases, one from M1 and one from M2. If your matrix is not connected, if it's disconnected, then you can split it into a sum like this, and if those two guys are not connected, then you can keep splitting and writing your matrix as a until you can't go further. So in that case, you get an expression of M as a sum of connected matrix, and it turns out that that expression is unique. So if you write your matrix as a direct sum of connected matrix, those are unique, and those are called the connected components of your matrix. And the theorem is that this also appears in work of Nick Ford. For positroids, the connected components can be told very easily from the core diagram, from this representation. So the connected components of a positroid are simply the connected components of this core diagram. What do I mean by that? I mean just the connected components of this red picture here. So for example, 2, 3 are going to be one component of this red picture, and that's why 2, 3 is one connected component of the positroid. 10 is going to be on its own in one connected component. These 9 and 6 and 8, 1, 4, 5 are going to be one component because these edges, these arrows cross over here. So all these guys are going to form one component here, and then 7 is going to be on its own. So this positroid here has 4 connected components. Okay, and here's the picture of connected components. And in particular, this description shows that the connected components of any positroid are going to form a non-crossing partition. You get a partition here of the numbers 1 up to n in such a way that the connected components, the parts, do not cross in this picture. Right? And that's, so any positroid has an associated non-crossing partition corresponding to the connected components. Okay. And for proving this, we use the description of positroids in terms of polytopes. For example, we use this condition here. How about enumerating connected positroids? Yeah, there are some nice enumerative results that follow from this description. Let's define P of n to be the number of positroids on the numbers 1 up to n, and Pc of n the number of connected positroids. It's not hard to count the total number of positroids on n elements. Okay? From this description in terms of decorated permutations, you can count how many decorated permutations there are with n elements, and you'll find that you get this number, which is of course very close to n factorial times e. Okay? From our description of connected positroids, we see that so these are all positroids. The connected ones are the ones that are in bijection with what are called stabilized interval-free permutations. So permutations such that in this diagram you only have one component. That means that the permutation cannot fix any proper interval of n. So 2, 3, for example, here it's a fixed interval of this permutation, and that cannot happen for a proper interval if we want to have a connected component. If we only have a connected positroid, only one component. So connected positroids are in bijection with safe permutations, and these kind of permutations have been studied in the literature already by Callan and Salvatore Torraso. And it turns out that this number, it tends, when n grows, to just the number of permutations with no fixed points. So the condition that it has no stable intervals is very similar to the condition of not having fixed points when n is very large. And we know what this number is, in what it is close to. This is just the number of derangements on n letters. This is close to n factorial over e. So as a corollary, one nice way of putting these two guys together is that the proportion of connected positroids over all positroids on the ground set n tends to 1 over e squared, because this is like n squared n factorial over e, and this is n factorial times e. So this is, yeah, 1 out of e squared positroids are connected. You have a very large ground set. But there is this conjecture for general matrix that the same ratio of connected matrix over all matrix tends to 1. So there is this, like, it's a different. So this is not evidence for this conjecture to be false or anything. This just says that positroids are a very special class of matrix, and they might behave differently. Let me skip this part and tell you about oriented matrix. So what is an oriented matrix? An oriented matrix is, well, how do you get an oriented matrix from a matrix with real entries? An oriented matrix is just a function that to every subset of n of size m, it gives you a sign, either minus or 0 or plus. And it just records the signs of the maximal minors in your matrix. Okay? An oriented matrix is some kind of combinatorial generalization of these kind of functions that you can get in this way. It's just a map that assigns to every subset of n either minus, 0, or plus, but it has to be combinatorially compatible with the Blooper relations. So forget about this part. This is the formal definition, but this is not very enlightening. What you should have in mind is that an oriented matrix is just an assignment of minuses, zeros, or pluses to the subsets in such a way that there is a chance for these Blooper relations to hold. So for example, if this product here is positive, then at least one of these two terms has to be positive. It's not possible that a positive comes from the sum of two negative terms. So that's what this condition is going to do. And then the oriented matrix that come from a matrix, from an actual honest real matrix, let's say n by n matrix, those are the ones that are called the realizable matrices, oriented matrix. But studying realizability is a hard problem for oriented matrices. So there is this belief that I'm calling belief here. It's a conjecture by them, and it was that the missing axiom of matrix theory is lost forever. So this is basically saying that there is no combinatorial way of characterizing the oriented matrix. There is no axiom that you can add to matrix theory in such a way that you characterize exactly which are the realizable matrices. And this is formally stated as a conjecture here. They prove some part of it, but it's still open, I guess. And over the rational numbers, studying realizability of oriented matrix over the rational numbers is particularly hard. So here's a theorem of Tromsø's that says that the existence of an algorithm for determining if an oriented matrix is realizable over the rational numbers is equivalent to the existence of an algorithm for deciding the solvability of arbitrary Diophantine equations over the rational numbers. So this is Hilbert's 10th problem over the rational numbers. And despite a lot of interest by number theorists, this is still open. We don't know if there even exists an algorithm. It doesn't matter the complexity. We don't even know if there's an algorithm for solving arbitrary Diophantine equations over the rational numbers. That's equivalent to determining if any oriented matrix is realized. And there's also an interpretation in terms of lattices, space lattices of cube polys. Well, it might be hard to study realizability for general oriented matrix, but there's a nicer class that are called positively oriented matrices. So these are the oriented matrices for which all subsets have a plus sign. All subsets get a plus. You're not allowing any minuses. So this is like the analog of positroid, but in the oriented matrix case. So these were studied by Hilda da Silva in order to generalize the combinatorics of the cyclic polytope. Because if you take a van der Monge in the matrix, then this condition is going to hold if you order the columns correctly. And she conjectured that every positively oriented matrix was realizable. So that just requiring this condition that all the subsets have a plus sign, a plus orientation, that already implies that there was an honest matrix that realizes this oriented matrix. And that's what we proved. So we proved that every positively oriented matrix, the underlying matrix of it is a positroid. And therefore, it is realizable over Q. So it follows from the work of Positroids that every positroid is not only realizable by a real matrix, but by a rational matrix, and then that implies this conjecture. And again, the idea of the proof is to use the description in terms of polytopes. If you assume by contradiction that you have a positively oriented matrix that is not a positroid, then a facet, and this should be an S again, A sub S, a facet of this form where S is not a cyclic interval is going to give you a contradiction with the combinatorial Kluger relations, with the definition of oriented matrix. Let me tell you one last interpretation or corollary of this theorem, that every positively oriented matrix is realizable. There is a natural order on oriented matrix called specialization. So if chi and chi prime are oriented matrix, we say that chi specializes to chi prime if the only subsets in which they differ, well, it's because one of the pluses or minuses in chi I becomes a zero in chi prime. Yeah, in chi becomes a zero in chi prime. So just take some of the pluses or minuses of chi and turn them into zeros. That's what specialization is. And then the Macphersonian, or the combinatorial Grassmannian, is simply going to be the poset of oriented matrix ordered by specialization. So this is some kind of combinatorial model for what the real Grassmannian should be. You just put all the oriented matrix in a poset, and then you look at the topological representation of this poset. So this was defined by Macpherson in order to study matrix bundles of combinatorial differential manifolds, so some combinatorial differential manifolds. And it's kind of a mystery what the topology of this poset is. So if n is equal to 1, 2, n minus 2, or n minus 1, we do know that the order complex of this poset is homotopy equivalent to the real Grassmannian. But otherwise, we don't know much about the topology of it. So Anderson and Davis made some progress understanding homotopy groups and some homology groups of the Macphersonian, but we don't know much more than that. So the big open question, I guess, is the Macphersonian homotopy equivalent to a real Grassmannian for any m? Or well, we can define the positive Macphersonian to be just the subset of the just the subposet of the Macphersonian consisting of the positively oriented matrix ordered by the same subset of positively oriented matrix. And this is a much nicer poset than the whole Macphersonian. So this is like the analog of the positive Grassmannian inside the Grassmannian. The positive Grassmannian is just a subset of the Grassmannian where all the Plucker coordinates are non-negative. And then it has a, as I was saying, it has a Positroid stratification that makes it a CW complex. This was proved by Positroids, Spire, and Williams. And I guess it's still open to show or to answer if it is a regular CW complex or not, but at least it's a CW complex. And the poset of cells in this stratification, so this is like the poset of positroids. It was studied by Lauren Williams, and she showed that it was graded thin and it was EL labeled or EL shell. Okay. So we know a lot about these positive positroids, and what we proved, or what follows from the result that every positively oriented matrix is a positroid, is that these two posets are the same. The positive Macphersonian is just the same as the positive positroids. And we know a lot about these positive positroids already. We know because of this that it's homeomorphic to a ball, for example. And then in this case, well, it's going to be homotopy equivalent to the positive Grassmannian because this space here is contracted, as was shown by these people. So what I'm trying to say is that we don't know too much about what the connection is between the Macphersonian and the Grassmannian. We don't know if their topology is related or not. But once we take their positive parts, the positive Macphersonian and the positive Grassmannian, we do know that we do know a lot more about them. We do know that they are homotopy equivalent, that one of them is homomorphic to a ball, and it's conjectured that this other guy is homomorphic to a ball. So I guess I'll stop here.
Questions for Felipe?
Is there an abstract axiomatization for positroids?
Sorry?
Is there a nice axiomatization for positroids without relying on the matrix?
Yes. So for example, there is a condition on the basis that tells you when a matrix is a positroid. Or I like this description in terms of the facets. You can take that as an axiomatization. There are some axiomatization for positroids, just purely combinatorial. And that's I guess what we use to prove all these kind of figures.
Also to follow up on that, so are you non-representable positroids?
Sorry, say that again.
Are there been non-representable positroids?
No, positroids by definition are just the ones that you can get from an actual honest matrix.
Oh, right, yeah.
And you look at the non-negative one. Yeah.
Was there a reason to think that positive-oriented matroids and positroids would be related in that way heading in, aside from that they both have positive?
I mean, this condition here is saying that somehow you want a combinatorial-oriented matrix where all the minors are non-negative, and that's precisely what a positroid is. So the difference between positively oriented matrix and positroids a priori is just the realizability condition. Since positroids are the ones that are realizable, and these more general things a priori include non-realizable ones, but what we show is that they are in fact just the same. But this condition is basically saying that all minors are positive or non-negative.
Does your work help resolve the conjecture that the positroid stratification gives a regular CW complex?
Not that I know of. No. This is this is still open, and I don't see why or how to apply these results to make more progress here.
So before we thank Felipe again, I will just tell you that we have a brief announcement. No?
Yeah, but thank you.
Yeah. Well, no, I just